Good. Hello, everybody. Today we are
take notes for me?
something called good.
Just like photocopy.
Good. Today we're going to do something called counting. Ready? You may already know something about this. You may already know something about this from previous experience with this, although it's not really in the middle school math curriculum as much as it should be, but you might know it from math team, from middle school math team, or from high school math team. It goes kind of like this. Let's do a little warm-up fake story. Suppose we are going to dress a toddler, like my daughter. She has 4, frozen shirts. And she has 3 sparkly pants. And she has 2 pairs of shoes. 2 pairs of shoes. How many outfits does she have? A lot. A lot. Could I get a numeric answer?
2.
Whoa.
24.
How many different outfits does she have, assuming her outfits require her to wear a shirt, a pair of pants, and a pair of shoes, and also all her outfits match?
2. Oh.
24 is the answer. Okay, so the explanation is extremely common sense, but we'll do it anyway because I think it's worth it. We are going to dress her in the morning. What should we do first? Well, first we should pick a shirt. How many shirts are there to choose from? 4. Woo! So 1, 2, 3, 4. So I'm making like a kind of like a tree. After we choose a shirt for her, how many choices of sparkly pants do we have?
3.
3. Woo! So 1, 2, 3. And if we chose the first shirt, we still have 3 choices for sparkly pants. If we chose the second shirt, we also have 3 choices. If we chose the third shirt, we also have 3 choices, and also 3 choices here. In other words, for each choice of shirt, there are 3 choices of sparkly pants. Agreed?
Agreed.
Okay, and then a pair of shoes, and there are 2 choices for what pair of shoes she wears. And the idea here is that her choice of her choice of shoe is independent of her choice of sparkly pants and frozen and shirt. And so for every choice of shirt, there are 3 choices of pants, and for every choice of shirt and for every shirt and pant combo, there are still 2 choices of shoes. Okay, is this all making sense? I mean, this should feel like blindingly obvious to you. This is called the fundamental principle of counting. Fundamental principle of counting says if you have 4 ways of doing one thing and 3 ways of doing another thing and 2 ways of doing another thing, then you have 4 times 3 times 2 ways of altogether. Yeah? Woo! Think of each of the choices as a path through a tree. This is kind of like the decision tree. So if you sort of feel yourself making the choices, then you can sort of feel yourself following one of the branching paths, and there are just 24 branching paths. Okay, questions on that? Say no. No. Good. That fundamental counting principle is professional camera work here. Whoa, hitting students. Oh yeah. This fundamental counting principle can then be used to solve all kinds of all kinds of very basic, simple kind of problems. Ready? Say yes. Yes. All right. Suppose I want to know how many numbers are there? Numbers between 2,000 and 9999 that are divisible by 5. Divisible by 5, and use unique digits. Actually, this might be too hard. How about divisible by? Let's just take off the unique digits part. That's better. How many numbers are there between 2,000 and 9999 that are divisible by 5? Okay, there are many ways to do this, including common sense, where you just sort of take all the numbers between 2,000 and 999. This is inclusive. And then figure that 1/5 of them are divisible by 5. But what I was imagining was kind of more of a digit by digit analysis. So consider the 4 digits of my number, because it's going to be guaranteed to be a 4-digit number, right? How many choices are there for the ones place, seeing as how the number must be a multiple of 5? 2 choices, because every number that's divisible by 5 has to be has to end in 0 or 5. How many choices are there for the first digit? 8, definitely 8, right? Because it can't be 0 and it can't be 1 because it's got to start with at least 2. So that's 2, 3, 4, 2 through 9. So I have 7 choices for the first digit. I have 2 choices for the final digit. How many choices do I have for these 2 middle digits?
You mean 8 choices for the first digit?
What's up? Oh, sorry. 8, not 7. 8. 8 because anything from 2 through 9. So anything but 1 or 0. Sorry. And then this digit? I think 10 now, right? Because it can be 0, right? Any number 0 through 9. So I have 10 choices. I have 8 choices for the thousands place. I have 10 choices for the hundredths place. I have, again, 10 choices for the tens place and 2 choices for the ones place. And therefore, since each of these digits is kind of each of these digit choices is independent of the others, then this says that I'm going to have 1,600 total numbers, which kind of makes sense because there are 8,000 numbers between 2,000 and 9,999, and 1/5 of them should be multiple. All right, good. Okay, let's do another one. Suppose we are making license plates. Let's suppose that we're in some state where every license plate consists of exactly 7 characters, and those 7 characters can be numbers or letters. So, capital letters of the English alphabet or digits. How many possible license plates are there?
36 to the
How many choices are there for the first character? 36. That involves another counting principle, which is that if there are 26 alphabetic characters and 10 numeric characters, then there are 36, alphanumeric characters. Okay, that's just the first digit. Second digit, or second character, I should say. Also 36, and etc., etc. So every single character of this 7-character string, there are 36 options. Therefore, there are quite a number of license plates. There are going to be like 36 to the 7. All right, good? Okay, let's do another one. Suppose I give you the word, take this word, sequoia. Sequoia. Do I know how to spell sequoia? I-O-A, is that right? That's probably right. Can you rotate that a little bit to make sure it's good? I guess it's like O-I-A. That looks better. Well, it's one of those two. Anyway, this is a cute little word of English. It's like a tree, also like a car. I think it's a tree, right? Yeah, it's a tree. And note that all 5 vowels of English are included in this 7-character word, so that's kind of exciting. Okay, suppose I was going to, suppose I was going to make words out of this, out of these letters, or strings rather. So here comes the question: how many 4-character strings can be made from these letters? Well, as written, it's a little bit ambiguous. What would you like some clarification? What clarification is required?
Can you reuse letters?
Can you reuse letters? Exactly. That's kind of important, right? So are these kind of like are these like wooden, like letters, or are these like stamps or something like that? Yeah. So if you can, suppose first that you can reuse letters. So this is like either like a typewriter or like a wooden stamp or something, or like a stamp pad or something like that. Then how many choices are there? If my string is going to be 4 characters long. How many choices for the first character? 7. How many choices for the second character? 7. Okay, etc., etc. So we have 7 to the 4th possible strings that I can make. But what if we can't? If we can't reuse letters, Then what? Chuck. Yeah. Exactly, then I have 7 choices for the first letter, and for each of those choices, I have to make a choice of the second letter. And the choice of the second letter, I now have only 6 choices because I've used one of them up. So times 5, and then times 4. 5 choices for the third letter, 4 choices for the fourth. Okay, alright, who's like with me? This is like just like basic intro, kind of general concept. Alright, good, I'm gonna erase this, and we're gonna pivot into like an extended example, which brings together some, 15 minutes? Alright, just gonna make this work. Okay, suppose that we have suppose that you are in high school and you have 7 academic classes. And those 7 academic classes meet every day, so we're in some kind of like all-period day school. And you have homework in all classes. Okay, so you're on the bus and you're on your way home and you're thinking, man, I gotta do all this homework. And you're just kind of like, you got 7 textbooks, on the shelf. And those 7 textbooks are like, like A, B, C, D, E, F, G, for example. What should the names of the classes be? A is for? Algebra. B is for? Biology. You can do goofy ones.
Cookbook.
C is for cooking. Okay. D is for?
Dog grooming.
Dog grooming. Whoa, you got that one. You felt strongly about that one. Good. E? Eating. Whoa. Okay, sure.
Face planting.
Whoa.
Food.
Okay, and G?
Gerrymandering.
I don't know. That's too long. Gerrymandering. All right, so this is a quite distinctive schedule that you have. Algebra, biology, cooking, dog grooming, eating, face planting, and gerrymandering. All right, a lot of important homework we got to do tonight. How many ways are there to do your homework? Different, distinct ways in which you are concerned with not just, you're doing homework, the order matters and all that kind of stuff. Answer. Yeah, let's not dwell on this because I think this one's kind of easy, right? You have 7. Think of it as 7 independent choices. And these 7 choices, just like the example of getting dressed in the morning, right? But now your outfit has 7 components to it. How many choices do I have for what class I do first? 7. But then I've already done one. So for every one of those 7 ways, how many choices are there for what to do next? 6. So for every one of those 7 ways of deciding which class to do first, I have 6 ways of deciding which class to do second. So there are sort of 42 ways to do 2 of my homework, to do 2 of my classes worth of homework, caring about the order in which I do them. Okay, and then? 5, 4, 3, 2, 1. Okay, so this is 7 factorial. 7 factorial, just what? Most people will simply define 7 factorial to mean 7 times 6 times 5 times 4 times 3 times 2 times 1, which is perfectly reasonable, and therefore this is the answer to this problem. In general, we call this a permutation. And so I'm going to just make a whole theorem. Let's call this theorem number 1. There are n factorial ways to permute n objects. So I'm introducing this word permute. Permute kind of just means scramble. A permutation of n of 7 things is a way of putting those 7 things into some kind of order. Cool? Okay, and so based on the example that we did above, I'm ready to state it as kind of a general idea that if you have n objects and you're permuting those n objects, then there are n factorial ways to do that. All right, the deep way of doing this, which we're going to kind of have to do in this class but not really, is to define n factorial to be the number of ways to permute n objects. And then it becomes kind of a theorem that n factorial has this as its like formula. Okay, if you got that, cool. If not, whatever. Okay, next. That was scenario 1. So this was like part 1 of the story. It's a 3-part story. Okay, good. Stop talking. Oh, all right, we are in part 2. All right, well, best laid plans, blah, blah, blah. You thought you were going to do your homework, but then, something intervened. You got home, you were hungry, you took a nap, you played video games, you went outside, it was a nice day. Other things, who knows, played sports, did other, helped old ladies across the street, whatever. Now, suddenly, it's 10 p.m. You haven't done any homework. It is now you no longer have enough time to do all your homework in all your classes. So you just got to cut your losses. So, we have only enough time to do 4. Okay, so now the new question is, how many ways can I do homework in 4 out of my 7 classes? All right, well, I think alone this is not a hard question, right? Let's just get right to it. Boom, 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 boom. How many choices do I have for which homework to do first? 7. Come on, you're trying to answer me?
Yeah,
Then?
6, 5, 4.
That's just for sure the answer, yeah? Okay, now, you could just leave it like that and call it a day and move on, or we could kind of dwell on this. So the answer is 7 times 6 times 5 times 4, which is, yeah?
7
Oh, you should like rotate a little bit.
Yeah, 7,
Right.
7 factorial divided by 3 factorial.
Yeah, so it's possible that some of you have done this before, in which case you might be familiar with this concept, but even if you were not familiar with this concept, you might find it sort of natural to kind of write this down in like a formula, because what if this weren't 7? What if this were like 25? Do you agree that it would be lame to write 25 times 24 times 23 times 22? Is there like a shorter way to write it? Well, yes. You can think of this as what happens if you multiply all the numbers by each other, starting from 7 going down. But then we don't go all the way down to the end. We like kind of stop at like 4, right? So we divide out by those last couple. All right, we okay with that? Okay, good. So this is a kind of a nice little sort of thing that comes up. Let's now generalize based on this little example, and let's just say that we call this. We also call this a permutation. So, and there's a name for this. We call this thing 7p3. No, sorry, 7p4. So, what is 7p4, or some people pronounce it 7 permute 4? Well, 7, not 7, let's do it in general. npk, you write it with these little kind of like subscripts, which we pronounce n permute k, but actually no one really does that, but you could, is, by definition, the number of ways to permute k objects from a set of n objects. So, just like in the example above, I have 7 classes to choose from overall, but I am only going to do 4 of them. Okay, and what have we sort of already seen now is the formula for NPK. Yeah. N factorial over, careful, it's n minus k factorial. Okay, so this formula is very important, and once again we could fall into the trap of kind of like leaning on this formula too heavily and not actually understanding it. Some people will even just give this formula out, which I kind of think is sort of terrible. Let's try to understand this formula, and we can try to understand this formula by translating it out of the language of division and into the language of multiplication. So what this formula is really saying, in other words, is that npk times n minus k factorial is n factorial. Okay, let's try to understand this. Well,
okay, hello Precalc C. We were in the middle of this video on fundamental counting principles. I did a really good job in 4th period, slowly and thoroughly doing this a little bit on Wednesday, and then very slowly and carefully Friday before the test. I didn't think to record it, and then came up with this amazing idea to record 8th period's version for 6th period to watch, but didn't really allow enough time for this. So 8th period got a kind of rushed, crappy version. Anyway, here we are. I also didn't think to just record back at Blair, so I'm back at my apartment, and we are going to finish this off. Hopefully this is going to be like 5 more minutes. So period 8 is watching from this point on, and period 6 is continuing. What did we do? A quick summary. This was the setup. We had a situation, a scenario in which we had 7 classes worth of homework, and we had 7 classes. We had homework in every class, and we can think of that as represented by sort of 7 textbooks. And now you're deciding how many ways are there to do your homework, and the answer was there are 7 factorial ways to do your homework, because you have 7 choices for what to do first, 6 choices for what to do next, etc., etc. Okay, and we summarize this with a kind of a theorem that there are n factorial ways to permute n objects. That's a new word for most of you. A permutation is just a way of scrambling all the objects, and so if you think of the 7 textbooks as, or the 7 classes starting with A, B, C, D, E, F, G, then that's just a string of length 7, and a permutation of those 7 characters is just some string, and it's just some string composed of those 7 characters, and there are 7 factorial, 7 times 6 times 5 times 4 times 3 times 2 of those strings. This is not a complete list. 7 factorial is a huge number, but this is some of the list. I made this exact list on the board. Okay, great. That I think is pretty straightforward. Then we moved on to scenario 2. In scenario 2, we're not going to do all of our homework anymore. We're only going to do some of our homework. There's only time now to do 4 classes worth of homework, or we decide that we're just going to do 4 classes worth. So how many ways? The question here is, how many ways are there to do 4 of the 7 classes worth of homework? And this was, I thought, also pretty easy. Okay, well, what homework are you going to do first? 7 choices, then 6 choices for the second homework, 5 choices for the third homework, 4 choices for the fourth one. So the answer to this, even if you had no background knowledge, I think is pretty straightforward. 7 times 6 times 5 times 4. If you had just solved this previous problem using the factorial notation, you might find it helpful to phrase this in terms of factorials. Okay, especially if this number were sort of very big, like 30 or something like that, it would be annoying to write out, 30 times 29 times 28 times 27, etc. And so we resort to this notation, which is that we represent 7 times 6 times 5 times 4 as 7 factorial over 3 factorial. Okay, great. Can I understand this on some deep level? I think we can, and I gave a kind of a decent explanation of this in period 8 in the video that came just before this, but it was starting to get a little bit rushed, so let me just kind of try it one more time. How should I understand 7 factorial divided by 3 factorial? Well, if there's some kind of division going on, then something sort of mysterious is happening. What is the sort of meaning of 3 factorial? What is the meaning of 7 factorial? Why am I dividing these things together? Okay, well, I think this is kind of the way to understand it. Think about all these strings. Like I said, 7 factorial is a gigantic number, so this would be a very, very long list. This is just a kind of a peek at part of it. What's going on here is that this is going back to scenario 1. In scenario 1, there were 7 ways, 7 factorial ways to do all your homework, so we were listing all of the options. And so since we're doing all of the homeworks, I kind of went all the way out to the end. And we see, A, B, C, D, E, F, G, A, B, C, D, E, G, F, A, B, C, D, F, E, G, etc. And here we have 6 of these that all begin with A, B, C, D. And they differ only in the last 3 homeworks. And it's not a coincidence that I have 6 of these. I have 6 of these because 6 is 3 factorial, or 3 factorial is 6. In other words, you can think of this original list, the list corresponding to scenario 1, as being naturally grouped into sections of length 3 factorial equals 6. And what do these 6 strings all have in common? They all have in common that they start with A, B, C, D, but they differ in the order of the last 3 classes. Okay, but in this scenario 2, in which we're not actually doing the homework in the final 3 classes, then what happens after we do our 4th homework is irrelevant. In other words, you could think of the final 3 characters of this string, you know, EFG, EGF, FEG, FGE, GEF, GFE, as sort of like irrelevant in some sense. They are irrelevant because we don't even do the last 3, okay? And so these 6 strings appear separately, correctly, as 6 different outcomes in the first scenario. But in the second scenario, they are really just one outcome, because now we're only doing 4 classes worth. In other words, you have to feel that this original list, the list that was 7 factorial long, is 6 times too long when applied to scenario 2. In scenario 2, since we're only doing, I'm just kind of repeating myself in 5 different ways here, since we're only doing the first 4 homeworks, and we're not doing the final 3, then the order in which you intended to do the final 3 is a kind of a moot point. All of these 6 separate entries should be considered the same entry. And so there's this kind of like fusion process in which we take all 6 of these and kind of condense them into just one thing. The appropriate list to answer the question that comes up in scenario 2 is a list which is 6 times shorter than my original list. Because for every single collection of 6 strings in the original problem that all end in the same 3 characters, they should all, those 6 should appear as just one entry in the list of all the ways to do 4 classes worth of homework. Because of course all of these are really just saying do A, B, C, and D in that order. Okay, so that is a good way to think about this division, right? 7 factorial is the number of ways to solve the problem in scenario 1. I divide by 3 factorial because that list is 6 times too long to answer the question that's being asked in scenario 2. And okay, you can sort of see this sort of continuing, right? Because I made another one. This is now A, B, D, C. And once again, there are 6, I guess it stops here. There are another sort of 6 of these. So there are 6 here, and there are also 6 here. But all 6 of these correspond in scenario 2 to the outcome, which is to do A, B, D, and C. And what comes after that is relevant. Okay, so that is normally how people teach this, and I think that's a fine way of understanding it. Also, let's just introduce some notation in general to abstract away from this problem. We did this in class. Let NPK represent the number of ways to permute K objects from a collection of N objects. And so this is just the general version of the problem that we just solved. This we would call 7, this is 7P4. Because I have 7 objects and I'm permuting 4 of them. So N in NPK is the answer to the question, how many ways, given a collection of N objects, are there to permute K of them? And if you just generalize the logic from a minute ago, you see that this is the formula that we've come up with. That the number of ways to permute K objects from a collection of N objects is N factorial, and then we divide by N minus K factorial, because if I'm permuting K objects, then there are N minus K objects that I'm simply ignoring. Think of N minus K as the number of classes worth of homework that we just simply don't do. And if N minus K factorial is the way of ordering those irrelevant things, then my original list is N minus K factorial times too long, and so I divide by that factor to correct. Okay, I find this proof to be really annoying, mostly because I find division kind of annoying, and actually understanding this with division is quite hard, although maybe you understood everything I just said. I think a much clearer way of thinking about it, I'm going to call this a proof. I'm just going to write it out and explain it in words. A more clear, in my opinion, way of understanding this theorem in the red box is that is to represent it as a multiplication problem. So what's going on here? Well, here we have k objects. NPK represents the number of ways to permute k of them. So I'm sort of deciding for my first k classes, how many ways are there to do my homework in k of my classes. And then, just for fun or something, I could also arrange all of the remaining n minus k objects. And so if I put the first k objects in order, and then I also put the remaining objects in order, well, for every way there is to put the first k objects in order, there are this many n minus k factorial ways to put the remaining n minus k objects in order. But now I have just ordered all the objects. I explained this in period 4 in terms of kind of like a museum. If you imagine a scenario in which there is a museum which is opening with some very popular exhibit, you know, some kind of prize artwork is on loan or something for a brief period of time and everyone wants to go. There are no tickets or anything because it's free, because it's DC, so instead just thousands of people line up outside the museum, you know, waiting to get in. And let's imagine that there are n people waiting outside to get in the museum, but there's only room inside the museum for k of those people. And so when the museum is about to open, they let in k people at first, and then throughout the morning, as people leave, then new people can be allowed in. So what is NPK? NPK therefore represents the number of ways of putting the k people that are allowed into the museum. It's the number of ways of putting those people in order. This is the number of ways to permute k of the n people. In other words, it's the number of ways to take the people waiting outside to put k of them into some kind of order and send them through the front door. But then we would also like to order the people who remain behind, because we don't want chaos outside the museum. We want the people that didn't make it in to be standing in a single file line so that they can enter one at a time as the people who are done leave. And so this factor represents the number of ways of putting k of the people in order. This factor represents the number of ways of ordering all the other people that don't make it in the museum. After all, n minus k people need to remain outside. Well, if you multiply the number of ways to put the k people who make it inside in order times the number of ways to put all the people that don't make it inside in order, you've in fact just ordered all n people. And so I think that makes complete sense. If you understand this thing in the purple box, then of course the theorem in the red box just follows from division. Okay, finally, to the point where we were when the video stopped. In scenario number 3, I changed the problem slightly. So with 2 minutes left before the bell rang or something, maybe I'll even edit this out of the old video. I asked how many ways are there to pick which 4 classes of homework to do. Okay, this is different here because now by using the word pick, I've implied that all that matters now is which 4 homeworks I do, not the order in which I do them. And okay, and so the answer to this question is going to be shorter. It's going to be smaller than the previous one in scenario 2. And okay, let's try to sort of understand this in some kind of way. Well, let's go back to this list again. Recall that I had this sort of very long list, this 7 factorial long list, and then we condensed it by a factor of 6 into this shorter list. And so these 6 strings of length 7 all became just the string sort of A, B, C, D as a solution to the problem in scenario 2. And these 6 strings, all of which were distinct as an answer to scenario 1, all became, when I condensed by a factor of 6 in scenario 2, all became A, B, D, C. Okay,
But I hope you now appreciate that for the purposes of answering the problem in scenario 3, these should still be considered the same. Because in scenario 3, I only care which 4 homeworks I complete, not the order in which I do them. And so whether I happen to do A, B, C, D or A, B, D, C, that's irrelevant to me. Because in fact, in both of those outcomes, I still just do those 4 homeworks as opposed to some different 4 homeworks. Okay, and so you can, if you're kind of catching the drift of this, answer this question just using some sort of common sense. And the answer is, let me take the number of ways, which was 7p4, to permute 4 of the 7 homeworks, and let me further divide. I'm now going to divide by 4 factorial. Because there are, after all, 4 factorial ways for A, B, D, and C to all swap places. In other words, what you have to do is that we have to imagine this list being much, much longer. 4 factorial is 4 times 3 times 2, so that's 24. There are 24 ways to scramble A, B, D, and C. A, B, D, C, D, A, B, D, C, A, C, B, D, etc. Okay? And every one of those every one of those 24 entries appears as a separate outcome in scenario 2. But in fact, in scenario 3, we want to consider them all to be the same outcome. And so therefore, the sort of the way to pull this all together is to realize that the list that corresponds to the scenario 2 problem is too long by a factor of 24 as a solution to the problem in scenario 3. And so the answer to the problem in scenario 3 is the answer to the previous problem, but divided by 4 factorial, because that list is 4 factorial too long. And we have a name for this. We call this 7 choose 4. And that's a nice little, we pronounce this 7 choose 4. And we write it like this. And what is it? It's the answer to the question, how many ways given 7 objects are there to choose 4 of them? And there's an alternative notation which looks like this. Okay, so to finally kind of put this all together and finish this off, I hereby define this symbol, n choose k, written like this. And what is n choose k? It represents the number of ways to select k objects from a set of n objects. And so now I'm just picking which objects to select. I am not permuting them. I am simply choosing them. Okay, and yeah, the theorem that generalizes what we just discussed a minute ago is that the number of ways to choose k objects from a set of n objects can be constructed as follows. Permute, let npk be the way to permute k objects from a set of n objects, and then sort of decide somehow after the fact that you don't care about the order of the objects that you selected. If you don't care about the order of the objects that you selected, because order doesn't matter, because we're just trying to decide which ones to choose, then there are k factorial ways internally to order the k objects that you picked. And so if the npk answers the question, how many ways are there to permute k objects from a set of n objects, I want to divide by k factorial because there are k factorial ways to order these, and so I want them to be sort of unordered. Alright, if you follow that, I think it's a little bit confusing, then this is the formula that you end up with. npk by previous work is n factorial over n minus k factorial, and then that whole thing is over k factorial. And so what we get is this formula, by simplifying the fractions, we get this formula that n choose k is n factorial over k factorial n minus k factorial. So that's like the theorem. I'm going to put a red box around this. Great. Of course, we could stop there, or just 2 more minutes, we can sort of argue that this is true in a way that I find less confusing
and that is to eliminate the division and to phrase everything in terms of multiplication. It all becomes therefore more clear in my opinion. So here is my proof. My proof is if you take the number of ways of choosing k objects from a set of n objects, let that be the definition, let that be the meaning of n choose k. There are this many ways to choose k objects. Well, then multiply by k factorial. What is k factorial? It's the number of ways of ordering those objects. And so if there are this many ways of choosing k objects and this many ways of ordering those objects, then when you multiply these two together, you get the number of ways of permuting k objects. And then if you also multiply by n minus k factorial, well, if you've chosen k of the objects, then there are n minus k objects remaining. If you put those in order also, well, now you've just ordered all the objects. And so this proof, once again, comes in a kind of talk it out sort of a way, is the sort of 10-second version of the proof is choose all the objects, then order them, then order all the ones that you didn't pick, and then you've just ordered all of them. Okay, a slightly longer explanation might resort to this museum scenario again. So once again we have n people waiting outside to get into a museum. K people only can fit in the museum. And so 5 minutes before opening, someone comes outside and says, okay, we gotta organize this, mess. They have this many ways, n choose k ways, to decide which k of the n people milling about outside are going to be allowed in. So you have this many ways of choosing which people are allowed in, but then, of course, people still need to enter one at a time through, say, a single door and, get their bags checked or whatever. So first we choose which k people are going to enter the museum, and then there are k factorial ways of permuting those k people to put them in a single file line so that they may enter. And for every one of the n choose k ways to pick k people, there are k factorial ways to order them, so that's why we multiply. But then, what about all the people that are left outside? There are n minus k of them who don't make it into the museum. Well, they also need to be put in order. Like I said before, we want them in a single file line so that they can enter one at a time as spaces free up. And so there are n minus k factorial ways of putting those people in order. So if there are this many ways to choose which k people enter, and there are this many ways to put those k people in order, and there are this many ways to put all the other people in order, then now by multiplying those together, we've just ordered all the people, and there are n factorial ways to put all the people in order. Okay, very thorough video. Hope that helped. Goodbye.